Hello. In this video, we're going to learn how to graph conic sections, specifically ellipses and hyperbolas, that have rotation involved. Specifically, we're going to learn how to use matrix algebra to graph quadratic functions of the form ax squared plus bxy plus cy squared is equal to 1. And specifically, it's this bxy term, which is going to lead to the rotation, as we'll see. This video does assume that you have some knowledge of matrix algebra. Specifically, we're going to need eigenvalues and eigenvectors, some diagonalization results, and knowledge of transposes and symmetric matrices. But before we dive into all of that, let's start off by doing a bit of review of something you might have learned in an algebra class long ago. So first, we'd like to talk about graphing a function of the form ax squared plus by squared is equal to 1. And specifically, we're going to be interested, at least first, in the case where both a and b are positive. And so a is greater than 0 and b is greater than 0. So one of these cases might be quite familiar. So for example, if a is equal to b and they're both equal to 1, this is a graph of the unit circle. You're left with x squared plus y squared equals 1, the unit circle. If a and b are equal to if a and b are equal to each other, but both equal to some number other than 1, you get circles of different radii. But in general, the graph you will get for such an equation is going to be an ellipse. Now, in graphing these functions, we typically like to rewrite the equation ax squared plus by squared equals 1 in a different form. Specifically, we're going to rewrite this function in the form x squared over alpha squared plus y squared over beta squared is equal to 1. In other words, right, the coefficient of x squared, a, we're replacing that with 1 over alpha squared. And if you want to find out what alpha is, you can solve that expression for alpha, and you will find that alpha equals 1 over the square root of a. This is one of the reasons it's very important for a to be a positive number. Similarly, the original coefficient of y squared was b, and we're writing that as 1 over beta squared. If you solve for beta, it follows the same pattern. Beta is equal to 1 divided by the square root of b. Once again, that's why we need b to be positive. Now, what do we know about the equation if it's written in this form? So again, the form of the equation is x squared over alpha squared plus y squared over beta squared is equal to 1. Well, there's a few points that we can identify as being on this graph right away. We could say the graph of this function contains the points where xy is equal to plus or minus alpha, comma 0, and also 0, comma plus or minus beta. Right, if we plug alpha in for x and 0 in for y, the left-hand side is clearly equal to 1. And similarly, if we plug in 0 for x and plus or minus beta for y, we'll get both sides of this equation equal to 1. So if I'd like to start drawing a graph of this function, and I'll go ahead and draw an xy axis here. And I can label a few points that I know are on this curve. And so this could be the point alpha 0. On the opposite side, this is the point negative alpha 0. Up here I have a point 0, comma beta. And down here I have a point 0, comma negative beta. So I know there's 4 points on it. And in general, this is the equation of an ellipse. So I'll just draw a smooth curve connecting these 4 points. And so this distance along the x-axis from the center to the rightmost edge is alpha. The distance from the center, or the origin of the ellipse, to the top, that distance is beta. And typically our ellipses will look a little bit more smooth. That's about the best I can draw there. So that's the equation of an ellipse. There are other cases as well. It might not be the case that both A and B are positive. Another possible case, what if A is less than 0 and B is less than 0? Well, in that case, the equation ax squared plus by squared is equal to 1 has no solutions. Because no matter what you plug in for x and y, you will get positive numbers, and they're both being multiplied by negatives. So you know that the left-hand side of that equation is negative, the right-hand side is positive, so there's nothing to graph in that particular case. The other two cases are kind of symmetric. The case when one of A and B are 0, and when one of A and B are positive and the other of A and B are negative. We won't actually be considering the case where either one is 0, because if A is equal to 0 or B is equal to 0, then again, you'll have either no solutions or maybe 1 or 2. All right, so for our next case, let's do the case where A is greater than 0 and B is less than 0. In this case, you can take the equation ax squared plus by squared equal to 0, and you can rewrite it in the form x squared over alpha squared minus y squared over beta squared is equal to 1. All right, so to start, we do know a few points this graph contains. Right, the graph of this function contains the points x comma y is equal to plus or minus alpha comma 0. And if you plug in plus or minus alpha for x and 0 in for y, both sides are clearly equal to 1. However, unlike the first case, this graph does not contain the point 0 comma plus or minus beta. And if you were to plug in 0 for x and beta for y, you get -1 on the left and +1 on the right. So that point does not make the equation true. That point is not on the graph of this function. So how do we get an idea as to what this function looks like? Well, the idea here is we're actually going to try to take this equation and we're going to solve the equation for y. All right, so I'll start off. I'm going to move the y squared divided by beta squared onto one side, and I'll move the 1 onto the other side, and I'll end up with y squared over beta squared is equal to x squared divided by alpha squared minus 1. Again, I'd like to solve for y, so I can multiply both sides of this equation by beta squared, and then take the square root of both sides. So I'll do a few algebraic steps here. Solving for y, I'll get y equals plus or minus the square root of beta squared divided by alpha squared x squared minus beta squared. All right, now this may seem a little bit, I don't know, counterintuitive or unintuitive. What happens if I try to calculate y divided by x? Right, y divided by x, That's going to be plus or minus 1 over x times the square root of all these terms. And what I'd like to do is actually bring the 1 over x inside the square root. But if I bring that inside the square root, it'll get squared. And I'll have to distribute 1 over x squared to both of those terms. And we'll find out that we're left with plus or minus square root of beta squared over alpha squared minus beta squared over x squared. That's y over x. Now, what's really interesting about this is what happens if we take the limit of this expression. And I don't really want to go on to the next slide, so sorry for going over to the left here. What happens if I take the limit as x goes to infinity of this expression? Or in other words, what happens when x gets larger and larger? What happens to the expression y over x? Well, in this expression, right, on the right-hand side, the only place you have an x is in the denominator of this fraction. And as x gets large, dividing this term, this right fraction, by x, by a large number, sends that fraction to 0. That fraction gets smaller and smaller. So you're left with plus or minus square root of beta squared over alpha squared minus 0. Okay? Subtracting 0 from something doesn't change the number at all. So you're left with plus or minus the square root of perfect squares in the numerator and denominator. So we're left with plus or minus beta over alpha. So what is this telling us? On the left, we have y over x. You can think of that informally as the slope of this function. Right? As you travel out to infinity in the x direction, right, this expression, y over x, tends to plus or minus beta over alpha. Right? So we actually have an asymptote, which is going to help us. Asymptote. Oh, that's not spelled right. Asymptote. There we go. So this will actually help us produce a graph of the function. Right? We have 2 points that the graph contains, right? Plus or minus alpha, comma 0, and we have an asymptote. So let's go ahead and draw a graph of this function. And so I would like to graph the function x squared over alpha squared minus y squared over beta squared is equal to 1. We're going to put together that information we have from the last slide. We know a couple of points on this function. We know this contains the point alpha 0 and the point negative alpha 0. And we also know, going to mark beta and negative beta on the y-axis. Right, there's actually some asymptotes for this function that we're aware of. Right, as the function gets larger and larger in the x-axis, the ratio of y to x gets closer and closer to this line. The slope of this line, the dashed green line I just drew, is beta over alpha. And because you might be able to see that contains the point beta comma alpha. So we could calculate the slope. Right, and similarly, I have a asymptote going in the other direction as well. So these aren't actually points on the function, but just kind of guidelines. But as the function goes to infinity, the function curves out towards these lines asymptotically. This function is called a hyperbola. And similarly, there's another case where you have, in this case, alpha less than 0 and beta is greater than 0. In this case, you're able to rewrite the original quadratic function as y squared over beta squared. This time the a is negative, so minus x squared over alpha squared is equal to 1. In this case, you can draw the function using the same logic, just reversing the roles of x and y. And you know there's 2 points that are on your function, and those points are, not beta, but 0 comma beta, and 0 comma negative beta. Similarly, if I mark off alpha and negative alpha on the x-axis, it's going to help me position some asymptotes. All right, and over in this direction, up in this direction. And so as we go out to infinity in the x direction, you know that the curve is sloping out like so. Honestly, that's not a great hyperbola, but this is really just a review. All right, so those are some of the basic quadratic functions, but all of these fall into the case of a function that looks like ax squared plus by squared equals 1. Right, we haven't talked about the term xy. Right, what if our quadratic function looks like that? How do we know what that graph is going to look like? So again, I just want to remind you of the ultimate goal here. The goal is to understand how to graph functions of the form ax squared plus bxy plus cy squared is equal to 1. Right, so now we know if we have an x squared and a y squared term, we know how to graph that. But what effect does this term in the middle, this xy term, have on the graph of the function? And it turns out one way we can really understand what's going on is by the use of matrix algebra. So in particular, for what's following, I'm going to assume that we have some background knowledge here. I like to assume knowledge of, first, eigenvalues and eigenvectors. Eigenvalues and eigenvectors of a matrix. In other words, if we have a matrix A times some vector V, sometimes that might be equal to a constant lambda times the vector V. That's not always true, but sometimes it's true. And in that case, V is called an eigenvector and lambda is called an eigenvalue. In particular, we're very interested in two variables. So V, or W, will be two-dimensional vectors having an x and y component. And so the matrices we're going to be interested in are 2 by 2 matrices. There will typically be two eigenvalues, each with its own corresponding eigenvector. So we'll need to know how to calculate that. We'll also need to know a little bit about diagonalization. Right, if you are able to find enough eigenvectors and eigenvalues for your matrix, you can write the matrix A in the form P times D times P inverse, where P is the matrix whose columns are eigenvectors. So the first column has the entries for my eigenvector V. The second column has the values from the eigenvector W. And D is a diagonal matrix which contains the eigenvalues, lambda and kappa, from top left to bottom right. And it turns out you can check just by multiplying it out that if you have eigenvalues and eigenvectors, as shown here, you can diagonalize the matrix. You can write it in this format. Finally, the other information we need is knowledge of something called the transpose of a matrix, which is when you interchange the rows and columns, and the properties of a special kind of matrix called a symmetric matrix. A symmetric matrix is a matrix which is equal to its own transpose, denoted by A to the T. So here T isn't a number, it isn't a power, but it indicates that the transpose of a matrix is equal to itself, the rows align with the columns. And in that case, again, in the 2 by 2 case, it turns out that the eigenvectors are perpendicular to each other. In other words, the dot product of the eigenvectors is 0. And furthermore, when you choose eigenvectors, any multiple of an eigenvector is still an eigenvector. Right? So if also you choose your eigenvectors so that they're both normal or they're both unit vectors, they both have length 1. And so if that's also true, then it turns out that the matrix P is a rotation matrix. And because you have 2 perpendicular vectors, right, V and W, and they both have the same length, and they represent the image of the unit basis vectors I and J. So for reasons which are best found in another video, P is a rotation matrix, and you can also see that P inverse is equal to P transpose in that case, which will turn out to be a very useful property. All right, so again, going forward, this is the knowledge we need. And so you might be wondering, how does this tie in to the quadratic functions we were looking at earlier? In one hand, we have a matrix. On the other hand, we have these quadratic functions. And so now we'd like to relate, quadratic functions to matrix algebra. So we're going to be looking at something called quadratic forms. So basically, what I'd like to do is to rewrite the function ax squared plus bxy plus cy squared in a strange way. It's going to seem more complicated at first, but it's going to turn out to be extremely useful. So I'd like to write this as xy a b over 2 c times xy. Now, it might look very different, but if you actually multiply these things out, then you'll see that you actually get that quadratic function. And if I start out by multiplying the matrix and the vector on the right, I'll be left with xy times, let's see, ax plus b over 2y for the top entry, and b over 2x plus cy for the bottom entry. And then multiplying together these two terms, we'll get ax squared. And I've got to multiply that x times the entire top there. So b over 2xy plus, I need to multiply y times the bottom part of that vector. So plus b over 2xy plus cy squared. And sure enough, when you add up the b over 2 terms, they're going to combine to give you bxy. And so this is actually equal to the quadratic function. In general, we'll write this a little bit shorter. And so what I'd like to do is think of v as the vector of variables xy. And if v is that vector, then v transpose, turning that single column into a single row, is the matrix xy. So functions of this form can be written like so. They'll typically be written as q sub a of the vector v, and this is v transpose times a times v. Right, so above in our example, we're interested in the case where the matrix A was equal to A, B over 2, B over 2, C. In theory, you could build a function like this for any matrix A, but we'll mostly be interested in quadratic forms where the matrix A has a special form. In particular, you might notice that that matrix is symmetric. That's going to be important later on. And so, big note, for this matrix, A transpose is equal to A. It's got some nice symmetry there. All right, so again, just we have it all on one page. The function q sub A of v is equal to v transpose times A times v. And we also know that A is A is symmetric, which also means that we can write A, we can write as PDP inverse, and P inverse is also equal to P transpose. All of these facts are going to become important. Now, another thing I'd like to define, which is something you're familiar with, but I'd like to do a formal definition all the same. The graph of a function. So in this case, the graph of QA times, and I'll write out the vector v, it's xy, right? The graph of this equation is the set of points xy that satisfy the equation. Right? We talk about equations a lot, and a graph is just a set of points. And so it's slightly different. Graphs and equations are related, but technically they're distinct mathematical objects. All right, so now I'd like to do a series of statements. And so if the point xy is an element of, so I'm using this symbol, if it's an element of the graph of QA, now I'm writing QA as short for QA of xy is equal to 1. And so this I'm going to denote as just QA to make this a little bit shorter. If xy is on the graph of QA, that means that Q sub A of xy must be equal to 1. That's the definition of being on a graph. Now that's true if and only if, well, let's use the definition of the quadratic form. So this is true if and only if QA, if the vector transpose xy times A times xy is equal to 1. But we can keep going. We know something about A. In this case, we're going to be able to diagonalize A as P d P inverse. So we'll substitute that in for A. All right, I'm going to go on to the next page. I'm going to write off where we left off, rewriting what we just had on the previous slide. The row xy times P d P inverse times the column xy is equal to 1. Okay, now I'm going to write a couple of things in a seemingly strange way. Again, it's completely equivalent. Right? So the row vector xy is the same thing as the column vector xy transpose. And another interesting fact is that if you do the transpose of a transpose, then they cancel each other out. So I'm going to replace the matrix P with the matrix P transpose transpose, which is still the same matrix. So P transpose transpose, I'm going to leave D alone, I'm going to leave P inverse alone, times xy is equal to 1. Next, I'm going to use another fact about transposes. All right, what I'd like to do now, and I want to draw your attention to this part of the previous line, I'd like to kind of factor out a transpose to be informal. I'd like to pull out one transpose from each of those terms. And a transpose of a product is the product of the transposes, but in the reverse order. Right? So if I want to pull out a transpose, that's okay, provided that I reverse the order of whatever is left on the inside. In other words, I can rewrite that parenthesized term as the transpose of the quantity P transpose times xy. All right, and still I have P inverse xy is equal to 1. Now again, we're in a very special situation when A is a symmetric matrix, which means that the eigenvector matrix P satisfies P inverse is equal to P transpose. So I could further write this as P transpose times xy, the entire quantity transposed, times D times P inverse xy. I'd like to parenthesize the P inverse xy. And what I'd like to do is actually, on that very first matrix P, P transpose is equal to P inverse. So I can replace P transpose with P inverse. And what you might notice now is that I have the same quantity appearing twice. Right? I'll underline it. I have P inverse xy appearing 2 times. So I'd like to say, let W equal P inverse xy. And so what are we left with here? We're doing something called changing coordinates. And here I have W transpose times D times W equals 1. And once again, this looks like a quadratic form, except now we have W as the input for the form. Instead of the matrix A left in the middle, we've kind of grouped terms, so the only matrix left in the middle is that matrix D. So I could actually rewrite this as the quadratic form with a matrix D of W is equal to 1. Right? And this is true. Well, that's another way of saying that W is on the graph of the quadratic form Q sub D. But you might remember that W is P inverse of XY. And really, XY, we had also originally written that as V. So here, I can substitute W for P inverse of V is on the graph of the quadratic form QD. Now what I'd like to do is move this P inverse to the other side. And so this means that V is on, well, the graph of a form. A graph is a set of points. So P inverse V is in that set of points if V is equal to P applied to that graph. And remember, P is a rotation matrix. And again, because we started out with a symmetric matrix A, we know that the eigenvector matrix P corresponds to a rotation. So what is this saying? Let's go back a slide for a moment. When we started off, right, we started off with a statement, XY is in the graph of QA. Right, we want to know what this graph of this quadratic form looks like. We want to figure out a criterion for when a point is on that graph. And after a lot of algebra, right, we're left with this statement here. Right, so to summarize it up, right, XY is on the graph. Let's not say on, let's say it's an element of the graph of QA, the original quadratic form, exactly when XY is an element of the rotated graph of what we're going to see is a simpler quadratic form. But this is the key takeaway right here. This is worthy of stars, of being circled and underlined multiple times in your notes. All right, so what we should do is, well, I'm a big fan of the saying you learn math by doing math. We should do some examples and see how to actually use this result to draw some graphs. And so we'll do two examples. One of them will be a hyperbola and one of them will be an ellipse, just so we can kind of see the two big cases. All right, so first example. Let's say we want to graph. All right, let's graph and let's describe it in words too. The quadratic function x squared plus 10xy plus y squared is equal to 1. Now, if it wasn't for that 10xy term, it would just be a unit circle. But let's see what we can do here using the abstract formulas we've just been discussing. The first thing I'd like to do is rewrite it as a quadratic form. We're going to rewrite this using the powers of matrix algebra. And so the coefficients of x and y, you think of those as kind of both being ones. So I can rewrite this as the row vector xy times 1. And I want b over 2. Right? So remember, this is think this is A and B and C here. So I have 1, 10 divided by 2 is 5, 5, C is 1, times xy is equal to 1. And so this is our quadratic form. And so A is the symmetric matrix 1, 5, 5, 1. Next, what I'd like to do is diagonalize this matrix. So I'd like to find some eigenvectors and eigenvalues. Let's start off by finding the eigenvalues. And to calculate that, I remember I'm going to take the determinant of A minus lambda I and set that equal to 0. So I have the determinant of 1 minus lambda, 5, 5, 1 minus lambda. It expands out to 1 minus lambda times 1 minus lambda minus 5 times 5. So this becomes 1 minus 2 lambda plus lambda squared minus 25. So lambda squared minus 2 lambda minus 24. Set that equal to 0. Let's see, how does this factor? 24, I can factor this as lambda minus 6 and lambda plus 4. So this tells us the eigenvalues are 6 and 4, or 6 and negative 4. One of those I'll keep calling lambda, the other one I'll call kappa later on. All right, next page. So we have plenty of room to calculate the eigenvectors. So remember, A is the symmetric matrix, 1, 5, 5, 1. And I have lambda equals, I'm going to check the signs, lambda is 6. I want to next solve A minus lambda times I times an eigenvector V is equal to the 0 vector. And so let's see, I'll have A minus lambda I, so that'll be minus 5, 5, 5 minus 5 times xy is equal to the 0 vector. So if I expand that out, it's minus 5x plus 5y equals 0. And as always happens when we solve for eigenvectors, we have a redundant system of equations, meaning that we have a free variable. I'd like to pick x equals 1. And if x is equal to 1, y is also equal to 1. So that is an eigenvector, but I'd also like it to be a unit vector. So since the length of this vector, right, the length of v is equal to, let's see, square root of 2, instead I'm going to choose, instead let's let v be the vector 1 over radical 2, 1 over radical 2. And so there's our first eigenvalue and eigenvector. Next, let's do the eigenvalue, kappa equals negative 4. We're going to solve for A minus kappa I times vector W equals 0 vector. And so now I'm subtracting negative 4 from each. Well, subtracting negative 4 is like adding 4. This will be 5, 5, 5, and 5. It's a lot of 5s. Times xy is equal to 0, 0. Let's get 5x plus 5y is equal to 0. Right, I could pick negative 1 and 1. But again, I'd prefer to choose a multiple of this vector that is a unit vector. The calculations that follow, the length of the vector w is square root of 2. So instead, let's normalize this vector. We'll let w equal, divide each component by the length. All right, so we have our vectors v and w. We can now diagonalize. Right, P is going to be the matrix of eigenvectors. And so I'll have 1 over rad 2, 1 over rad 2 for the first column, negative 1 over rad 2, 1 over rad 2 for the second column. I remember writing A as P times D times P inverse. So next, D is the diagonal matrix with eigenvalues. The eigenvalues we found were 6 and negative 4. Right, so we found eigenvectors and eigenvalues. We've diagonalized it. Now, here's the fun part. Right, so the original quadratic form, right, what QA, V equals 1. A was the matrix, 1, 5, 5, 1, which corresponds to x squared plus 10xy plus y squared is equal to 1. Now we also have another quadratic form we can consider, QD of V. And D is the diagonal matrix 6, 0, 0, negative 4. Now if we were to expand this out, we would end up with 6x squared plus 0xy minus 4y squared is equal to 1. And this 0xy, we don't really need to write that. So instead, what we have is 6x squared minus 4y squared is equal to 1. And we know how to graph that. We can graph that. It's a hyperbola. Right, so in order to graph that, well, maybe at first I'll go ahead and rewrite it. Right, I would prefer to rewrite it in the form x squared divided by, it's going to be 1 over radical 6 quantity squared minus y squared divided by 1 over radical 4, that's 1/2 squared is equal to 1. Now this we can graph without too much trouble. It's not going to be a perfect graph, but we can definitely make some progress. So radical 6, let's see, that's about 2 point something. Since it's 2 point something, that's going to be a little less than 1/2. And so maybe I'll draw that point right here. Let's label alpha equals 1 over radical 6 to make this diagram a little less cluttered. So this is alpha 0. Let's draw another point over here. This is negative alpha, comma 0. And then we can draw a point at beta, not a point, but we can draw some kind of a guideline at beta, where beta is equal to 1/2. Right, that's a little bit larger because 1 over radical 6. Radical 6 is a little bit bigger than 2. So 1 over radical 6 is a little bit smaller than 2. And so this point up here would be 0 beta. I have a point down here, 0, negative beta. So we could draw some asymptotes. These dashed lines like so. So here's our hyperbola corresponding to the graph of the quadratic form Q sub D. And so this is Q sub D of V is equal to 1. However, you might remember from a few slides ago that we're interested in the graph of Q sub A of V. And so Q sub A of V, rather that graph, is equal to the rotated graph rotated by P. So P times, let's say P times the graph of Q sub D of V. In other words, we want to take this nice graph that we've drawn, we want to rotate it by whatever the amount is specified by the rotation matrix P. And so P is 1 over radical 2, negative 1 over radical 2, 1 over radical 2, 1 over radical 2. Now, there's a couple of ways to think about this. One way is, well, this is a rotation matrix, so we know we can write it like so. And so here we have cosine theta aligns with 1 over radical 2. That could tell us that theta is 45 degrees. However, it could also tell us that theta is negative 45 degrees. And to figure that out, if it's positive or negative 45 degrees, we'll need to look at the sine terms as well. Right? Because of the this, I like to informally think of this as the negative sign's in the correct position, so it's rotating by the positive angle. If instead the negative was in the lower left instead of the upper right, then I'd be rotating by a negative angle. And so that could be a little bit confusing to think of it that way. So another way we could think about this is this matrix, the matrix P, we can think of this as rotating, but we can also think of it as transforming the vectors I and j, the unit basis vectors, right? So P times the basis vector I gives you the eigenvector V, and P times the basis vector j, 0, 1, gives you the second column, gives you W. So what this matrix is doing is it's rotating I into the position of the first column, and it's rotating j into the position of the second column. So in order to draw the rotated graph, I'm going to go ahead and draw a nice big coordinate axis. What I'm going to do, let's see, maybe I'll do this in orange. I'm going to go ahead and draw the eigenvectors, the eigenvector V. This is 1 over radical 2, 1 over radical 2. And the eigenvector W, we know that's perpendicular to V. It's one of the cool things about diagonalizing symmetric matrices. This is the eigenvector W, which is negative 1 over radical 2, 1 over radical 2. In other words, this is like a 45-degree angle right here. All right, so what's happened is we've taken our graph of our hyperbola, we've rotated it in this way. Think of the eigenvectors as your new axes, and you actually want to graph your hyperbola using these as your axes. And so now I'm going to reproduce the graph over here of this hyperbola. And so I graphed this in blue, so I'll continue to graph it in blue over here. At this point right here, that's the point which is alpha away from here, right, where alpha was 1 over radical 6. So this distance is still 1 over radical 6. And this distance right here, let's say that's 1/2. And I need that so I can draw my asymptote. Through those lines. And similarly, we'll have symmetric lines all around. Get an asymptote there. Asymptote here. So now I can draw my function like so. Oops. Let's try again. I'm trying to have it asymptotically approach those lines. All right. That's really not a great looking graph, but it contains all the essential ideas. It's rotated by some amount, as illustrated by the eigenvectors, and we're able to give an idea of what that looks like. Excellent. So the second example, since we've had the practice of the first example under our belts now, the second example should go a little bit more quickly. All right, so next example. Let's try to graph the following quadratic function. 3x squared minus 4xy plus 6y squared is equal to 1. Now I can rewrite this as a quadratic form as follows. Right, 3, half of -4, half of -4, 6 times xy is equal to 1. Right, first step is to just rewrite it using matrix algebra. Next step is to take this matrix, which I'll call A, and I want to diagonalize that matrix. So we need to find eigenvectors and eigenvalues. Right, to find the eigenvalues, as always, we're going to do the determinant of A minus lambda times I. And that's going to be 3 minus lambda, -2, -2, and 6 minus lambda. We're doing the determinant of that matrix. So we will get 3 minus lambda times 6 minus lambda minus -2 times -2. Expanding this out, we'll have 18 minus 6 lambda minus 3 lambda plus lambda squared. All those negatives minus 4, which means that, let's see, we'll have lambda squared minus 9 lambda. See, 18 minus 4 is plus 14. It's equal to 0. Let's see, 14 becomes 2 and 7. So lambda minus 2, lambda minus 7 equals 0. Our eigenvalues are 2 and 7. And from this, we can actually say a few things already, skipping ahead a bit. Right, we know the diagonal matrix is going to be 2, 0, 0, 7. We know that the graph of this quadratic form is an ellipse. Right, because this quadratic form corresponds to the equation 2x squared plus 0xy plus 7y squared equals 1. Right, since the coefficients of x squared and y squared are both positive, and there's no xy term, we know we're going to get an ellipse there. But we want to use matrix algebra to figure out how much that ellipse has been rotated by. And so to do that, we need to continue and find the eigenvectors of this matrix. So remember, the matrix A is 3, -2, -2, and 6. First eigenvalue is lambda equals 2. So we want to solve A minus lambda I times vector V is equal to 0 vector. All right, so subtracting 2 from the diagonal entries, we have 1, -2, -2, and 4 times xy is equal to 0, 0. As always, we have a redundant set of equations. We have x minus 2y equals 0, and minus 2x plus 4y is equal to 0. So we have a free variable. I would like to choose x equals 2, which forces y to be 1. Right, so an eigenvector would be 2, 1. That's a solution for xy. There are lots more. In particular, I want to scale this one down by the length. Right, so the length of this vector is radical 5. So I'm going to divide out by its length, leaving us with a vector 2 over radical 5, 1 over radical 5 as our first eigenvector. The second eigenvector, again, we'll calculate it out for practice, but we already know that W is going to be perpendicular to V, and it's also going to be a unit vector, so we could theoretically solve for it here. Similarly, we can have a good guess at, since we have a cosine theta and sine theta in this vector, right, this represents the first column of a rotation matrix, we could also deduce the angle from there as well. But I do enjoy doing math. So I'm going to keep going, and it'll also help as a confirmation of what we're doing to make sure there's no numeric error here. Let's do our second eigenvalue, which is kappa equals 7. Now we're solving A minus kappa times I times the eigenvector W equals 0. So I'm subtracting 7 from the diagonal entries. We'll get -4, -2, -2, and -1 times xy equals 0, 0. And so we have the system minus 4x minus 2y equals 0, minus 2x minus y equals 0. So I'd like to choose the solution xy equals, let's see, simple numbers here. So let's do maybe, what about -1 and 2? Right, that'll work. And then, again, the length. This is radical 5, so I'm going to divide that vector by its length to get my second eigenvector. -1 over radical 5 and 2 over radical 5. We might have been able to guess that because we can see V and W, these two vectors, are perpendicular because their dot product is equal to 0. So that's great. So if we want to graph this, right, remember graphing, 3x squared minus 4xy plus 6y squared is equal to 1. All right, we want to rotate the graph of QD of V is equal to 1. And D was a diagonal matrix consisting of the eigenvalues 2, 0, 0, 7. Right, so that means this quadratic form is equivalent to 2x squared plus 7y squared is equal to 1 by the rotation matrix of eigenvectors. Going back to remind ourselves of what those were. 2 rad 5, 1 rad 5, negative 1 rad 5, and 2 rad 5. And again, you've got a couple of ways you can go about solving this. You could use some trigonometry to calculate the angle, or you can consider the columns of this, the eigenvectors, as your new coordinate axes. All right, so let's go ahead and graph. I'm going to start off by drawing my eigenvectors here. Let's see, 2 over rad 5, 1 over rad 5. And so let's see, the x is twice as large as the y, so it's going to be something like this. So this is my first eigenvector v. Then my second eigenvector is going to be perpendicular to it. And I think of these as my new coordinate axes. They've been rotated by some amount, theta, which again, you can solve for that. Cosine theta is 2 over radical 5. So if you really wanted a numeric approximation, you could most certainly find that. And next, I need to graph the function we have here. And I would write that as x squared over 1 over radical 2 squared. So that's my alpha is 1 over rad 2 plus y squared over 1 over radical 7 quantity squared is equal to 1. So here beta is equal to 1 over radical 7. 1 over radical 2, that's about 1.4. 1 over radical 2 is 1.4. Let's see, 1 over radical 7, I'm dividing by a larger number, so that's going to give me a smaller result. And so again, not perfectly to scale. You know that this length here is going to be 1 over radical 2. This length here will be the smaller 1 over radical 7. And again, it's an ellipse. It's nice and symmetric around the origin. And so there we have it. So we've learned how to graph rotated conic sections, that is quadratics which include that xy term, using a little bit of matrix algebra.